Okay, our next talk will be by Manki Kim, speaking about towards quantum gravity in realistic universes.
All right, is mic on? Okay. First of all, I'd like to thank the organizers for inviting me to give a talk at Pappalardo Symposium. It's my great honor to be able to give a talk about what I've been thinking about in the past 3 years. And then I want to take this as an opportunity to thank Neil and Jane for giving me this generous support. Thanks to your support, I was able to work on very risky projects, and many of them failed, but one thing really panned out, and that's the thing that I want to talk about. So before I go into the details of the talk, I want to first give you a high-level summary of the talk. What I really want to understand is how to do quantum gravity in realistic universes and in our universe and realistic cosmologies. As we all know, it's been very difficult to do cosmology in string theory, and there are many good reasons. And even if you succeed in finding a realistic cosmology in string theory, there's one thing that is really disturbing, which is that even in those cosmologies, we do not really know how to quantize gravity and how to compute quantum gravitational effects. There are many reasons why we cannot do so at this moment. And one of the core challenges is that to construct such cosmologies, you need to use stringy generalization of magnetic field. And in such magnetic field backgrounds, we cannot quantize strings. And therefore, we cannot understand quantum gravity therein. So this is really disturbing to me, because we spend all that time and energy to construct realistic cosmologies in string theory, and all that we can do is classical gravity. Then what have we done, really? So I really think that we should do something about it. And one thing that I want to highlight today is string field theory. String field theory is great because it allows you to study generic backgrounds, and you can study quantum gravity in generic backgrounds using string field theory. And with the help of string field theory, I studied a simple toy model that has the following features: 4 large dimensions and magnetic fluxes in 6 small dimensions. And unfortunately, we have some supersymmetry. But still, I would say it's a very nice starting point, because now we can finally understand how to quantize gravity in magnetic flux backgrounds. Hopefully, in the future, we'll be able to generalize this to more realistic cosmologies, say our universe. Okay, so this is the plan of the talk. I'll first talk about the motivation, and I'll tell you what string theory is, and then I'll tell you why it is difficult to do string theory in, say, realistic universes. And then I'll talk about string field theory and how we can use string field theory to study magnetic backgrounds. And then I'll conclude. So as I said, what I really want to understand is how to do cosmology in our universe. And there are many epochs of cosmological history, but what I really want to focus on today is this early time where the quantum gravitational effects become very important. And in particular, there are many mysteries that we do not really know how to answer or understand within the current formulation of gravity, let's say. For example, we do not really know what really happened in the early universe, and we do not really know how to think about how the universe began and how the inflation began. And that is related to the so-called measure problem. And the related problem is, why is the dark energy so small? We often hear about that, but I'm not going to really talk much about it. So to really understand the mysteries of the early universe in the early universe cosmology, in a way, we really need to understand quantum gravity in our universe, not in a fictitious universe. And we know that string theory is famously giving you the tools to study quantum gravity, so the natural question to ask is, can we use string theory to do cosmology? Unfortunately, it is quite hard to do cosmology with string theory if you're trying to do string theory in a conventional way. There are many reasons. We only know how to deal with small quantum fluctuations of space and time in string theory. And of course, in cosmology, that doesn't have to be the case. And we do not know how to quantize strings in time-dependent background, for example, when the inflation is happening. And we do not know how to quantize strings with positive dark energy. So we don't know how to do strings in our universe. And all of those problems are amplified by the fact that to do realistic cosmologies, you need to include magnetic fluxes, and then we don't even know how to do string theory in magnetic flux backgrounds. And today I'll talk about the first and the fourth problem in more detail and where I'm going with it. So, what is string theory? To talk about string theory, I'll first take a step back and let's talk about quantum mechanics. When we're doing quantum mechanics, we roughly do the following. Say you want to study a point particle moving between point P1 and P2. In classical mechanics, what we do is to solve the equations of motion and predict the path between P1 and P2, and that's what we do in classical mechanics. In quantum mechanics, what we do is to allow the particle to move through some paths that are not classically allowed. And that could also include some more drastic paths. And the rule to compute such probabilities of a point particle moving through some classically unallowed path is by using this path integral, where you're integrating over all the possible paths, and each path is weighted by the action. And if you minimize the action, then you can get the classical path. That's what we do in classical mechanics. What about gravity? What I want to do is roughly the same thing. But now I have the space-time, and I have some initial condition for the space and time, and I have the final condition for space and time. So what Einstein taught us is that if you solve the Einstein's equations of motion, then you can predict how the universe evolved in time classically. Now, if you want to do quantum gravity, what you need to do is to allow the space and time to evolve in time in a manner that is not allowed classically. For example, you can also include the possibility where a universe creates a baby universe and then it is collapsing back to the original universe. So conceptually, it is quite simple. Unfortunately, though, we do not really know how to write down the path integral measure for the gravity. If you're trying to do so, you find all kinds of pathologies like UV divergences. And perhaps we need to take one more step back and try to think of some simpler problem. So what I'm going to do is a simpler problem. I'm not going to allow some drastic topology changes. All I'm going to include is those little ripples of the universe. And by those little ripples, when I say perturbative, I mean those tiny ripples, not drastic topology changes. Then the question that I want to ask now is, can we understand and describe such small quantum fluctuations of space and time? And that's where string theory comes in. String theory gives you a way to describe those small quantum fluctuations. For example, what you do in string theory is as follows. You draw some strings, and you quantize strings. And you think about classical propagation of strings, and that corresponds to classical evolution of space and time, roughly. And now what you can do is to study quantum propagation of string in space and time, and that corresponds to small, tiny ripple of the space-time. The nice thing about string theory is that we have the path integral measure for a point particle, and we have the path integral measure for the strings. So we know the rules of the game, and then we can use this known rule to study quantum gravity. So this is where string theory comes in. But string theory is not perfect. The one thing that I need to really tell you is that the original universe in which string theory was formulated is very unrealistic. It is nothing like our universe. This universe is 10-dimensional. This universe has supersymmetry. For example, this universe doesn't have any dark energy, and it doesn't even have any dark matter. So if you really want to use string theory to understand our universe, we need to first find a realistic solution in string theory before we start talking about quantizing gravity. And there have been many attempts and many proposals to find such cosmologies, realistic cosmologies, which date back to this famous paper KKLT you might have heard of. Although it's been very challenging to realize such cosmologies, I would say we have seen some rapid progress in recent years. Although I'm not going to talk about the details of those progress, I like to stay, in a way, optimistic that in the near future we might be able to see some realistic cosmologies in string theory. then now the real difficult question is the following. Suppose that you have those solutions. What do you do? And there is something that almost no string theorist wants to talk about. So here's what you can do. You grab a random string theorist and ask them, I give you a digital solution or I give you a realistic cosmology. What can you do that a reasonable GR person cannot do? A disturbing thing that you'll hear is that, well, not so much. We don't even know how to quantize gravity in such cosmologies. And the reason, one of the very reasons why that is happening is because we do not know how to quantize strings in magnetic flux backgrounds. So we should really fix that problem before it's too late. Okay? Of course, I'm not going to talk about the details of the problem, but here is the rough picture. So say that you have a string that is propagating in a magnetic background. When you're trying to write down the theory of string, here's what happens. This is the so-called action principle. And then when you try to write down the action principle for strings in magnetic flux background, you get some non-local action. And when we have a non-local action, we do not know how to quantize the theory. It is simple as that. It's just the simple fact that magnetic flux is spanning around space and time, and when you're trying to understand strings going through magnetic flux, you have some non-locality. So all you can do in such backgrounds is classical gravity. So how can we fix the problem? What I would like to really emphasize is that the difficulty really lies in the fact that we're trying to quantize strings directly. When you think about E&M and quantum electromagnetic dynamics, we have no problem with dealing with magnetic fluxes. We know how to quantize them. But when you're trying to quantize strings, then you have a problem. So a good thing to do, Barton might say, is that maybe you can just directly quantize space and time. And then you don't have that same problem of non-locality. And that's where string field theory comes in. So the idea of string field theory is really simple. And at this point, you might be confused because I told you that writing down the path integral measure for gravity is very difficult, but now I'm telling you that it might be possible. So how is that happening? The idea is as following. So what I told you is that string theory gives you a perturbative way to describe quantum ripples of the space and time. Then when you want to write down the path integral, what you want to do is to know how to write down quantum fluctuations, infinitely many different possible quantum fluctuations. So what string field theory tells you to do is to just compute this scattering amplitudes or propagations of strings infinitely many times and combine them all at once. And once you do that, you'll get the path integral measure for space and time. The only downside of string field theory is that now you have infinitely many fields and infinitely many terms in your theory. But I would say that's a little disturbance, not a very big problem. But anyhow, string field theory gives you a way to directly quantize space and time, and it doesn't suffer the non-locality that we're seeing in the direct quantization of strings. For example, you can just perfectly well solve the equations of motion in the magnetic flux background, and then you can quantize the theory. And each term, so I'm not going to really explain what those mean, but every term gives you a Feynman law for computing quantum gravitational effects. And as I said, a little downside is that there are just infinitely many terms and infinitely many fields. But one thing that I really want to emphasize is that string field theory also has the potential to become non-perturbative. There is some hint or indication that maybe string field theory can also describe drastic topology change of the universe. So I think it is really a good thing to think about, string field theory is. So with string field theory, what I did with my collaborator Min-jae is that we found a four-dimensional solution in string field theory with magnetic flux. In this solution, the universe looks like four dimensions that are large, and there are some small, tiny six-dimensional torus. And crucially, there are some magnetic fluxes in the torus. As I told you, there are infinitely many terms and infinitely many fields, so you need to solve equations of motion infinitely many times. It sounds horrendous, but in fact, it is not that difficult. And as a little teaser, there is one particular field that is a solution to the equations of motion that looks like this. You don't have to really unpack that. What I want to just show you is that you can solve the equations of motion. And then now what I want to really stress is that we can finally compute quantum gravitational amplitudes in such magnetic flux backgrounds. So I would say it's quite exciting. And unfortunately, this background preserves some SUSY, but this is a unfortunate bug. So let me conclude. Understanding quantum gravity in semi-realistic universes is a very important open problem. One core challenge in string theory was to quantize gravity or quantize strings in magnetic flux backgrounds. With string field theory, you can actually now quantize gravity. And now we can do so many different things that we thought were impossible. So I would say it's a very exciting time for us. And hopefully, we'll be able to generalize it to more realistic universes. All right, thank you, Neil and Jane.
Thanks, Manki. OK, so we're open for questions. Neil, would you like to start?
I apologize, but no matter how much I try to study beforehand, this is a very difficult subject. How many of the current staff of physicists in the department can help you? I've seen I know one, I do have this picture.
Yes.
On the slide. How many other physicists can help?
Well, I would say as long as they have learned quantum mechanics, they can help me, as long as they are dedicated. It's not very difficult. People say quantum gravity is difficult and computations are challenging, but that's because we don't know the answer yet. Once you know the answer, you will say it's easy or understandable. So we just need to push enough so that we understand the answer, and then we can now look for different problems. But yeah, as long as you have learned quantum mechanics, you can do it.
Wolfgang, can you use the mic up there?
I have a question. When you emphasize that you wanted to make string theory compatible with magnetic fields, did you really mean magnetic fields, or do you mean some sort of gauge theories in general? Because at least in our world, in atomic physics and such, usually magnetic fields are weak and are not a problem. So I'm really surprised that you feel magnetic fields are a problem in, the high energy domain. But of course, magnetic fields are just the simplest example for maybe vector potentials and gauge fields.
Yes, so that's a great point. Actually, one of the other core challenges that I didn't mention is that those magnetic fluxes in string theory are quantized. So you cannot make them arbitrarily small. These are some integer valued things. But still, there is a way around it and then make it small. But the problem is really then, how do we deal with the non-locality? Of course, you can say that, well, those non-localities are still small effects. Why don't you just, do computations ignoring it or somehow, approximating things? But we just do not know how to deal with those when we have some non-locality. But maybe there is a way around it, but I don't know.
Alan, you first, and then Bob.
Hi. I'm not sure if I heard the final word on the status of dark energy in your model. Is it negative, 0, or what?
In my solution,
Yeah.
the solution that I studied in detail has 0 dark energy, but it is easy to generalize this kind of method to negative dark energy. Now, the real challenge is to generalize this to positive dark energy. For that, we need to do a lot of work. So I don't know how many years will take, but I'm hopeful that before I retire, we'll get to see the solution, hopefully. but I cannot
Try to
promise
do it
you
before
that.
I retire.
Yeah.
Bob?
Well, Alan actually stole my first question, so I'll ask a different one. In your world, which is supersymmetric, how difficult a problem is it in breaking supersymmetry and dealing with the consequences for the dark energy or the cosmological constant in a world with broken supersymmetry?
Yes, actually, the reason why I started doing this computation was to basically understand that. So there are some ways that you can break supersymmetry in string theory. But the crucial question is, okay, you broke supersymmetry, how stable is your solution, right? And then typically those questions involve quantum fluctuations. And then you should be able to compute quantum fluctuations in like magnetic flux backgrounds to really understand whether or not you have broken supersymmetry just the right way so that you have increased the energy, but your solution is still somewhat stable. So that is the goal that I'm really hoping to understand. At this point, I don't really know, but with this tool now, since now we can compute the quantum amplitudes, we can probably answer it in a definite way.
Sorry, this is maybe a very naive question, but why is supersymmetry a bad thing? I was under the impression that a lot of particle physicists think about supersymmetric theories as sources of new physics.
Well, supersymmetry is not a bad thing, but so it doesn't matter whether or not you have some supersymmetry at high energy scale, but for sure, for a realistic solution, we shouldn't have any supersymmetry left in the low energy. For example, the reason is that when you want to have a realistic cosmology that is time dependent, by definition, supersymmetry better be broken. And then that's the goal that I'm chasing towards. So supersymmetry is not a bad thing if you want to understand a particular problem, but what I really want is a solution that doesn't have supersymmetry.
It's also bad because we don't see it.
Yeah. Well, we haven't gone up enough, Like if you go to build like a galaxy-size LHC, but of course that's not going to happen, but yeah.
You said a realistic universe, right? So it's
Yeah, exactly. Yeah, I don't want Susie.
You mentioned string field theory being useful for non-perturbative effect. Can you give an example of something you'd like to calculate that's non-perturbative that you might hope to do in string field theory?
Yes. So at this stage, it is purely aspirational. I don't know how to do this computation, and I don't think anyone does. But what I really want to understand is string theory allows many different dimensions, right? It can be 1 dimension, 2 dimension, 26 dimension, it can be whatever. But why do we live in 4 dimensions? Is there any dynamical selection principle? You just start with some random dimension and then does string theory somehow select you 4 dimension? That's kind of a computation that I really want to understand. And then that involves topology change and drastic changes of space and time. And hopefully string field theory will tell us something about that.
Any further questions? Okay, Manki, thank you very much.
Thank you.